Hello everyone in Chemistry 40S and Chemistry 40SH. It's Dr. Carroll. We're looking at Unit 5, Lecture 2. We're all about the solubility product constant today. So, in your booklet, go to Unit 5, Lecture 2, and we were looking at what's called the KSP solubility product constant. It really is just an equilibrium constant. Not to be confused with KFC, which is Kentucky Fried Chicken. Okay, so KSP, it depends on the temperature just like any equilibrium constant does. It doesn't have units like any equilibrium constants. It is applicable mostly for sparingly soluble salts. Sparingly soluble is also known as insoluble. And you have to create the solubility equation to determine the value of KSP from the KSP expression. It's like we talked about the mass action expression before. KSPs are typically small numbers. Here I just wrote in 10 to the minus 90 to 10 to the minus 3. So those are typical values for KSP. You might think, oh, this is such small amounts, we don't really care about it. But small amounts of nasty chemicals in water can cause problems, just like various lead compounds. So you want to know how much can dissolve and how much of other chemicals is needed to remove some of the junky stuff that's in your water. So this is actually practical. It is relevant. So let's look at a few skills here. I arbitrarily have numbered them. So skill number 1, we are looking at how do you get the KSP value if you're given some solubility data. Okay, solubility data meaning a saturated solution, the numbers associated with that. So let's start with silver chloride, which is used in some photographic filming. The old days they had something called photographic film. And so let's jump to this example here. Silver chloride. Suppose you're given that the solubility of silver chloride is 1.4 by 10 to the minus 6 moles per liter. You want to calculate the value of the equilibrium constant expression. Here we go. You start by writing the solubility equation, which is AgCl goes to Ag plus Cl minus. And then your KSP, well, that is a KEQ, right? KSP, also known as the solubility product constant, or sometimes just called the solubility product, is just an example of an equilibrium constant. So it is Ag plus aqueous times Cl minus aqueous. And if you want, you can divide by 1, because you got a solid on the left-hand side. But that's sort of silly to divide by 1. It's just makes things muckier to look at. So just write it as Ag plus aqueous times Cl minus aqueous. Now after a while in this chapter, some students say, oh, do I really have to put in the aqueous in KSP? Because I know it's got to be aqueous. So fine, you can avoid putting the AQ if you really want. But I would still put it in at least the first 400 times that you do it. And the 401st time, you can switch. So if I know that I can dissolve in 1 liter 1.4 by 10 to the 6 minus 6 moles, or 1.4 micromoles, right? Then I would form 1.4 micromoles of Ag plus and 1.4 micromoles of Cl minus. So you would have those values, you plug them into your KSP, right? Your Ag plus and your Cl minus. So 1.4 by 10 to minus 6 times 1.4 by 10 to minus 6, and it's 1.96 by 10 to minus 12. Typically, KSP values are expressed in tabular form, first of all, and then in standard scientific notation, typically to 1 or 2 decimal places. You aren't going to go to more than 2 decimal places in standard scientific notation when you do a KSP. Okay, let's go to the second example here. By the way, this was page 6. This is page 6 of your booklet if you can't find it. Here we're looking at the solubility of calcium hydroxide. Calcium hydroxide is a strong base, but it has to get dissolved first. I'm going to assume, unless told otherwise, that all stuff in this chapter is at 25 degrees Celsius, because KSP depends on that. So if I write the solubility equation for calcium hydroxide, I'm going to get CaOH2 solid goes to Ca2 plus aqueous plus 2 OH minus aqueous. So if I dissolve 1.3 by 10 to minus 4 moles per liter of calcium hydroxide, then I'll get 1.3 by 10 to minus 4 moles per liter of calcium 2 plus. It's a 1-to-1 ratio. But in every calcium hydroxide, there are 2 hydroxide ions. So I get 2 times 1.3, 2.6 by 10 to the minus 4 of the hydroxide. So those are my equilibrium concentrations in a saturated solution of calcium hydroxide at 25 degrees Celsius. Suppose that is the information. Then to get KSP, you just plug into your KSP expression. So KSP is calcium 2 plus times OH minus squared. So it's 1.3 by 10 to the minus 4 times 2.6 by 10 to the minus 4 squared, and you get a KSP of 8.8 by 10 to the minus 12. Okay? Some students think somehow they're cheating, that they say, oh wait, no, I'm doubling it, so now I'm doubling the hydroxide and then squaring it? That can't be right. And to that I say, what do you mean it can't be right? That is right. That is the expression for KSP, calcium 2 plus times OH minus squared. And you have to get the equilibrium concentrations of your calcium 2 plus and your OH minus, and then you plug them in. Here's a you try, so you can pause the video here and try it yourself. I'll count to 3, 2, 1, 0, pause. And now we're back, and now let's do it. So here we go, Hg, OH2, mercury. That's not that commonly used here, but let's do it. So HgOH2, so that's going to be Hg2 plus aqueous plus 2 OH minus aqueous. So my KSP is Hg2 plus aqueous times OH minus aqueous squared. So at equilibrium, my Hg2 plus is going to be 4.3 by 10 to the minus 14. And my OH minus is twice that. Oh, I can do that in my head. So can you? 8.6 by 10 to the minus 14. So then my KSP is 4.3 by 10 to the minus 4 times 8.6 by 10 to the minus 14. 4.3 by 10 to the minus 4. 4.3 by 10 to the minus 14. 10 to the minus 14, right? 8.6 by 10 to the minus 14 squared. So let us punch that out here. 4.3 by 10 to the 14 times 8.6 by 10 to the 14 minus squared. 3.18 by 10 to the minus 40. Or well, let's go to 1 decimal. Keep Ms. NATO happy. 3.2 by 10 to the minus 40. Okay, so that is known, by the way, as a 1 to 2 ionic compound because I have 1 cation for 2 anions. The first one I did, AgCl, would be 1 to 1. If I had 2 cations and 1 anion, it would be 2 to 1. So you have 1 to 1, 1 to 2, or 2 to 1. And our next, I think, is going to be on page 7, 1 to 3. Oh, and it's upside down. How about that? Here, let's go. Let's have some fun here and try to make it right side up live and in person. And I got to do it one more time here. And one more time. And now I've got to go up a bit to page number 7 and see if I have flipped it the right way. And so we're going to look at an example which isn't 1 to 2 or 2 to 1, but rather is 1 to 3. So here we go. And of course it's still upside down. So aluminum hydroxide. Okay, I'm going to try it one more time. This is page 7. Rotate to the right. Rotate to the right again. There you go. I pressed it too long. Now I got it. So that was a sneak preview of things. The grams to mole. Why am I even talking about that? Because sometimes solubility isn't expressed in moles per liter. It's expressed in grams per liter or grams per 100 mil. And that's what we're going to do in our third example, aluminum hydroxide. Remember, grams to moles, you divide by the molar mass. So let's say aluminum hydroxide has a solubility of 3.5 by 10 to the minus 5 grams in 100 mils of a solution. We want to get KSP. And the first thing we're going to do is convert to moles per liter. So the molar mass of aluminum hydroxide, you just take the molar mass of aluminum plus 3 times oxygen plus 3 times hydrogen. You get 78 grams per mole. By the way, they'll be doing you're going to need lots of molar masses in this chapter to speed things up. There's molar mass calculators on the internet. There's one, I believe it's by Lentech, Lenntech, and you can search for that or just type in molar mass calculator in the Google, and you can quickly type in formula and they'll give you the molar mass. In fact, there's even apps for that. Of course there are. So I'm going to take my 3.5 by 10 to the minus 5 grams, divide by the molar mass, which is 78 grams per mole, get a value, and then I want it per liter. Well, 100 mils isn't a liter, it's a tenth of a liter, so I divide by 0.1, which is the same, FYI, as multiplying by 10. And I get 4.5 by 10 to the minus 6 molar. So you should be very adept at converting between grams per mil or grams per 100 mil or grams per liter to molarity, which is moles per liter. Okay, once you have the solubility, you can write the equation as solubility, Se. So it's AlOH3 goes to aluminum 3 plus aqueous plus 3 OH minus, because hydroxide, of course, is just 1 minus. I have 3 of them, so then aluminum has to be 3 plus. The solubility is 4.5 by 10 to the minus 6, so aluminum 3 plus is 4.5 by 10 to the minus 6, and the OH minus is 3 times that, so 1.35 by 10 to the minus 5. Okay, then the KSP is going to be 4.5 by 10 to the minus 6 times 1.35 by 10 to the minus 5 cubed, and I get 1.1 by 10 to the minus 20. So that is my value for KSP. Okay, so that's a 1 to 3. I could do a 3 to 1 as well. Let's go to example 4 here, which is the last of the possibilities. It's 2 to 3 or a 3 to 2. We aren't going to have a 2 to 4 or a 2 to 5 or anything like that. It'll either be 1 to 1, 1 to 2 or 2 to 1, 1 to 3 or 3 to 1, or 2 to 3 or 3 to 2. Those are the only possibilities for ionic compounds as related to KSPs. So here we have some unknown ionic compound. All I know is it's A2B3, and B is not boron. It's just a placeholder for the anion. First thing I read is the cation, so that is A in this case. Let's say the molar mass is 4 by 10 to the minus 8th. So I want to get the molarity and then take it from there. So I'm going to jump to here, 4 by 10 to the minus 8th grams. Now they give you the molar mass of this mystery ionic compound. So you divide by 226, and then you divide by 0.1, and you get 1.8 by 10 to the minus 9, or 1.77 by 10 to the minus 9. What does it say? Calculator pep talk on truncation versus rounding. What's that all about? If I take my 4 by 10 to the minus 8 divided by 226, I get 1.77 by 10 to the minus 10. Divided by 0.1, 1.77 by 10 to the minus 9, or 1.8 by 10 to the minus 9. Oh, I know what this is. If you aren't using your scientific notation, when you get into 10 to the minus 9, that's right at the limit of your display on most calculators. So it might just put a bunch of zeros and then a 1 as your last place on the right-hand side in your calculator display. That's known as truncation, not rounding. Truncation is wrong. You don't want to do that here. So bottom line is get into scientific notation at the beginning of these questions and take it from there. Because if you truncate this, it's 1 by 10 to the minus 9, and then if you go through everything, you're going to get all sorts of wrong answers. So be careful on that. Don't just like take your pen and muck up your calculator display and keep like going over, you know, little half circles like this right there. Oh, right, all that kind of stuff. That, and then first of all, it mucks up your display, and also it's wrong because it doesn't take care of the fact that you want to round and not truncate. Okay, so that was my pep talk. I hope you were inspired by that. So 1.8 by 10 to the minus 9. Now I'm going back here to the solubility equation. So A2B3, 1.8 by 10 to the minus 9. The A3 plus is 2 times that, so it's 3.6 by 10 to the minus 9. The B2 minus is 3 times that, so it's 5.4 by 10 to the minus 9. So my KSP is going to be my A3 plus squared. So 3.6 by 10 to the minus 9 squared times 5.4 by 10 to the minus 9 cubed. And you get 2 by 10 to the minus 42. 18 and 27, 37, 45, but we have this other stuff here. So if you're taking more decimals, it's 1.88 by 10 to the minus 42. Okay? Now, on to page 8, where we're going to try some skill number 2. And you can probably guess what skill number 2 is. It's the exact reverse of skill number 1. And there we go. So skill number 2, we're going to calculate the equilibrium concentrations in moles per liter, grams per 100 mil. Those are common ones. Grams per 500 mil is another one. Given KSP values, so you either get it in the body of the question or from a table of KSP data, and you calculate the equilibrium concentration given the KSP value. So let's jump right into it here. You're going to be using roots, by the way, here. Square roots, cube roots, fourth roots, fifth roots, and no more than fifth roots, though. Most of them will be not fifth roots, but we'll see. Here we go. So we got barium sulfate. KSP is 1.5 by 10 to the minus 9, and we want to get the molar mass for that. And there's the phone. Someone's going to grab the phone so that we don't get any private messages here. Okay, so that would be just too much information. Here we go. So we want to get the solubility. Let's start by getting moles per liter because those are the values we plug into our KSP. So just like in skill number 1, we start with the solubility equation. So BaSO4 goes to Ba2 plus aqueous plus SO4 2 minus aqueous. The value is 1.5 by 10 to the minus 9. That was given to you. So if we let X be the solubility of barium sulfate, then you're going to find at equilibrium, this abbreviated ice diagram, X moles per liter of barium 2 plus and X moles per liter of SO4 2 minus. So my KSP is going to be X times X, which is X squared, which is 1.5 by 10 to the minus 9, and then the square root of that is 3.9 by 10 to the minus 5. Or you can, if you don't like using square roots, so if you always like raising to the power, x to the y or y to the x, however your calculator displays it, square root is the same as raising to the 0.5 power. So at equilibrium, I will have 3.9 by 10 to the minus 5 moles per liter of barium 2 plus and 3.9 by 10 to the minus 5 moles per liter of SO4 2 minus. Now to get that into grams per liter, you're going to just multiply by the molar mass, right? Over here, we have 3.9 by 10 to the minus 5 moles per liter times 233.4 grams per mole. So the moles cancel, and I'm left with 9.1 by 10 to the minus 3 grams per liter. If I want in terms of 100 mil, well, it's going to be this of 4 here, right? It's going to be a tenth as much, right? 1,000 mils is the same as a liter. I could dissolve 9.1 by 10 to the minus 3. Well, if I only have a tenth as much solvent, I can just dissolve a tenth as much solute. So it's 9.1 by 10 to the minus 4 grams per 100 mil. And there's other ways to do that if you want, but this way is the most straightforward. Just think a little bit, right? A tenth of the solvent means a tenth of the solute to maintain our ratio, to maintain our values. Okay, so that's a 1-to-1 classic case. Now let's look at a skill 2 where it's a 1-to-2 case. So that is calcium fluoride, and the KSP is 1.7 by 10 to the minus 10 the molar mass. Oh, I was very nice, I gave it to you, but you could have got it from the periodic table or just one of your apps or that Lentech molar mass calculator. Very powerful program, and it's completely free for the next 30 days. Operators are standing by. Okay, so calcium fluoride goes to calcium 2 plus 2F minus. So if I let X be the solubility of CaF2, which I always do, then I get X of calcium 2 plus and 2X of F minus. So I plug that in, X times 2X, but I have to square the 2X, so it's 4X cubed, right? X times 2X times 2X is 4X cubed. Some students make the mistake and say it's 2X cubed. It's not, it's 4X cubed. So then 4X cubed is 1.7 by 10 to the minus 10. Divide by 4, take the cube root, and I get 3.5 by 10 to the minus 4. 3.5 by 10 to the minus 4 moles per liter. So that is my concentration of Ca2 plus. It's also the solubility of CaF2, and 7 times 10 to the minus 4, so that's 2 times 3.5 by 10 to the minus 4. That is the concentration of the fluoride. So my solubility, 3.5 by 10 to the minus 4, multiplied by the molar mass of calcium fluoride, 78.1 grams per mole, gives me 2.7 by 10 to the minus 2 grams per liter. Okay? Let's try this. You try here. HgF2, KSP is 6 by 10 to the minus 15. So that's a 1 to 2 ratio, right? If I do HgF2 goes to Hg2 plus 2F minus. So that's a 1 to 2 ratio. This is X, 2X, and KSP is going to be X times 2X all squared, X times 2X all squared. This is what I mean. X times 2X all squared, which is 4X cubed, which equals 6 by 10 to the minus 15. So then X is, I take 6 by 10 to the minus 15 divided by 4, and then I raise it to the 0.3333 power, right? It's the same as taking the cube root. 1.14 by 10 to the minus 5. So that's the solubility of HgF2. Okay, you see how this lesson basically writes itself. So we looked at 1 to 1, we looked at 1 to 2. Now we're going to look at 1 to 3. Let's just get the moles per liter. If you want, you can get the grams per liter and the grams per 100 mil. So we've got scandium hydroxide. Now scandium is not one we use often, but we know the charge has to be 3 plus because the hydroxides are 1 minus. So SCOH3 goes to scandium 3 plus 3 OH minus. My KSP is given as 4 by 10 to the minus 8. So I got X times 3X cubed. So that's 27X cubed times X. So 27X to the 4th is 4 by 10 to the minus 8th. So X to the 4th is 4 by 10 to the minus 8th divided by 27. And then X is the 4th root, which is the same as taking the square root twice, or the same as raising your 1.5 by 10 to the minus 9 to the 0.25 power. And you get 6.2 by 10 to the minus 8th. So we can put a little chart here how to calculate the solubility given the kind of ion you have. So if it's a 1 to 1, then the solubility is just the square root of KSP. If it's a 1 to 2 or a 2 to 1, then it is the cube root of KSP divided by 4. If it's a 1 to 3 or a 3 to 1, then it is the 4th root of, what is this? KSP over 27. And in the 4th example, this A2B3, if it's a 2 to 3 or 3 to 2, then to get the solubility, it's going to be the 5th root of KSP divided by 108. You divide by the 108 first, then you take the 5th root. So that little chart is going to be very helpful for you. So let me just put little grid lines in there so you see how it all works there. Okay, then you can just Google solubility chart has related to cation anion ratios, and you'll see this in a fancier fashion than my classic blue sketchings in the top right corner of this page. Okay, so let's look at a 2 to 3 one. So here's example 4. I have A2B3. The molar mass is given as 300 grams per mole. The KSP is given as 9 by 10 to minus 6. We want to calculate the solubility in molarity, grams per liter, and grams per 100 mil. So let's let X be the solubility. So I've got A2B3. Well, neither on the right hand side are just X. When I dissolve A2B3, however little or much I dissolve, I get 2 A3 pluses and 3 B2 minuses. Right? That's the only way that works. So I got 2X and 3X. So my KSP is going to be 2X squared times 3X cubed, which is 4X squared times 27X cubed. 4 times 27 is 108. X to the second times X to the third is X to the fifth. So X is going to be the fifth root of 9 by 10 to minus 6, which is my KSP over 108. And I get 3.8 by 10 to minus 2. So that's the solubility. And then I can plug that in to get my amounts of A3 plus and B2 minus. So right, my A3 plus will be 2 times 3.8 by 10 to minus 2. My B2 minus will be 3 times 3.8 by 10 to minus 2. And then to get the grams per liter, I just multiply by the molar mass, which was given as 300 grams per mole, and I get 11.4 grams per liter. And if I want it in 100 mils, well, that's going to be a tenth as much of the gram. So instead of 11.4, 1.14. Okay. Ooh, here we're going to try one together. Let's try this one here. At the bottom of page 9, we got A2B3. The KSP is 8 by 10 to minus 8. So that's a 2 to 3 ratio. So my solubility is just going to be the fifth root of 8 by 10 to the minus 8 divided by 108. So let's figure that out. 8 by 10 to the 8th minus divided by 108. And I'm going to raise to the 0.2 power, just same as taking the fifth root. On some of those TI graphing calculators, it's a pain. You have to hit second function math. You have to give your pin number and all this other information. This way, just raise to the 0.2 power is much faster. So 1.49 by 10 to the minus second molar. By grams per liter, I would just multiply the 1.49 by 10 to the minus 2 times 400. 5.97. That's a rather large amount, isn't it? But that's what the numbers say. 5.97 grams per liter, which is 0.597 grams per 100 mil. Okay. I think that's good for this lesson on KSP. The skills 3 and 4 we will do in our next lesson. So there will be some practice questions that I will put on Edsby to make sure that you are very skilled at everything there is to know about KSP. See you later.